My name is Goktug, and I'm a PhD student at the University of Louisiana at Lafayette. Today, I'm going to talk about our work, brain-inspired hypervector processing at the edge of large language model. So to give you an outline about the talk, I'll first mention our proposed method and what is the meaning of the edge of large language model. So as we all know, the language model has two phases. One is the pre-training phase, where you train a language model for a general task. And the other is the fine-tuning phase, where you train your language model to specify a certain task. So our goal was to eliminate that fine-tuning phase without all the extra layered neuron training mechanism to map those fields to the hyperdimensional domain. So secondly, I'll talk about how this affects us and what is the benefits of using hyperdimensional computing in terms of inference time on edge devices. So I'll mention also our overall results in terms of training results, accuracy results, and our memory usage of the model. And I'll conclude my talk with our general conclusion and takeaways from the topic. So for our use case, we picked the IMDb dataset and apply sentiment analysis with the HTC. How we did it is that, to give you a knowledge about IMDb dataset consists of movie reviews, mostly like 50,000 movie reviews, both positive and negative comments. And this data set is usually includes extremely lengthy sentences, so it's a challenging task for usually deep learning models to handle this sentiment analysis problem, even with the normal usual training base. So we took our base language models, BERT, DistillBERT, and GPT-2, to use their encoders to create a sentence embeddings. And in the next part, so usually in the second step, a language models is going to give us sentence embeddings in terms of encoder output to actually a numerical representation of each sentence in our dataset. So the usual vector size of these language models is 768, and we use those the normal in fine-tuning phase. Those sentence embeddings will go through training phase again with additional layers, and at the end, the model will able to make predictions. But that's actually the step we want to eliminate, and we wanted to use hyperdimensional computing. This is actually the third step. So how we did that is so as we seen in this hypervector in the third step, this 768 vector size represents the sentence embedding. So each index is a token here, and we wanted to map each index of the sentence embedding to hyperdimensional domain with hypervectors of size of 1000. So how we did that is that we actually normalize our sentence embedding to between 0 and 1. Then we decide on hypervectors for each index in the sentence embedding. So let's say our first index is 0.49. Our first index is 0.49. So 0.49 gets a specific hypervector that only contains binary values. So this is also another benefit. So in terms of hardware design, since our vectors are only binary values, we can design the hardware to do the hyperdimensional computing with just simple gates and maybe simple adders. So for the second index, let's say it's another point and another number, let's say 0.5. It is going to get another binary vector and also in the same size as the first one, so 1000. And we are going to do this for every index, every token in the sentence embedding. But the goal of the hyperdimensional computing is to create a holistic representation to represent the whole class and whole sentence. So in this case, we need to combine those hypervectors in a way so that only one hypervector can represent the entire sentence. So for the sentiment analysis task, we use the bundling operation. So we summed all the hypervectors that we assigned here to each index, and then binarized it again to work on the binary domain. And at the end, we end up with one sentence hypervector. So let's say we fit the positive comment to the model, and one positive comment will end up with one positive sentence hypervector. But the goal was to create only two class hypervectors. So in this case, a positive class hypervector and negative class hypervector. So those class hypervectors represents the whole sentiment. And we need to do the steps for every positive comment in the data set and sum them all again and binarize it. So this will give us only one hypervector that is actually called class hypervector that represents the positive class in the IMDb dataset. So this is actually the half of our model in the HTC space. So for the negative comments, we need to do the same steps again and assigning hypervector to each index, summing them, binarizing them, and then do the same step for every negative comment in the data set, then sum them again and binarize it, and we'll end up with, again, binary hypervector for the negative comments in the data set. So what this gives us is that instead of an additional layer in the fine-tuning phase, now we have only two hypervectors with a size of 1K that we can do predictions on. So there is no learning phase, there is no gradient, there's no derivation in there. There's just only hypervector assignments, summing them and binarizing them. That's it. So this is going to help us in the inference part, because after we create our model, for the test phase, for the inference phase, so let's say we get test data, and we are going to do the same step, first and second and third step, and we are going to binarize it, and this is going to be our test hypervector. And we are going to compare our test hypervector with positive class hypervector and negative class hypervector. And based on the similarity metric, the model is going to decide whether this test is positive or negative sentiment. So in terms of gains, we deployed 3 machine learning algorithms, random forest, SVM, and MLP, and also our HTC model on edge device. And in terms of inference times, our model is 3 to 6 times faster than those 3 others. So also this actually kind of proof of the possibility of using HTC on edge devices also for logical tasks. So usually the HTC is applied to the pattern recognition task, so without actually understanding the meaning of the sentence. So actually in this work, HTC is also understanding the meaning of words, why they consecutively put into each sentence and come up with a sentence. So in terms of overall results, so our model size is only 9 kilobytes. So this is because as a model, we only have 2 hypervectors and there is nothing else. So since there is no neurons, there is no weights, and there is nothing, there's just only 2 hypervectors, and model size ends up being only 9 kilobytes. So in terms of inference time, like I mentioned in the previous slides, we are faster in terms of 3 to 6 times faster than 3 other machine learning algorithms. And our accuracies, of course, like if you fine-tune a language model with a lot of layers and a lot of neurons, the state of the art for this problem accuracies can go up to like 95%, but that also comes with a cost. But if you compare our results with machine learning algorithms, not only we're beating them, but we are also on par accuracies with those models. And also in terms of training time, since this is only hypervector addition and binarization, there's no multiplication process, there's no derivation process. The training time is also faster for hyperdimensional computing, so that maybe in the future you can even train your HTC model on an edge device without the need of using powerful GPUs or maybe simple CPUs. So to sum up my talk, actually we want to show that HTC can be paired efficiently with the large language models using different base language models and can be applied to the language processing task that it can understand the sentiment behind each sentence. So also we wanted to show that with just small amount of model sizes, we can still achieve higher accuracies compared to the machine learning models. And another conclusion was to faster inference times on an edge device, that HTC can achieve this task extremely fast compared to the other models. And this is actually a general cost-effective method that everyone can use if they're like resource constrained, if they're like deploying model in resource constrained environments. So thank you.